So how is the screen sharing going on? Is it okay, or is it something funny?
It looks a bit funny. It's cut off on
it looks a bit funny.
Yeah.
Well, it looks funny.
We can only see part of the slide at the moment.
You only see part of it.
Yeah.
Well, I clicked on it. So maybe let me stop sharing and trying it once more. Okay, maybe it's that. Let's maybe try to make it smaller now. Okay, usually it works. How's that?
Okay, now we can see the.
Well, it's working. It's working.
I think
but
it works.
I cannot browse. What is really? Oh, it's working. Okay, so thank you very much for this wonderful invitation to this meeting. And yes, I keep up with the theme of this afternoon session, and I fully invite you to do some whale watching. And I think it's important, if you watch out for whales, even if you don't see anything, there might be a lot of life under the surface. And sometimes you see a tail, and sometimes you may see a whole bunch of it. Okay, so this is a talk about flavor physics. Okay, so I would like to open the stage a little bit about what that actually is, or how I'm actually seeing it. So you see something very familiar here. It's three fruit. Okay, so three things of the same kind. But of course, obviously, they are different in size, in color, and in flavor. And this is a bit what's happening with flavor in particle physics. They are the same for the gauge interactions. They are actually the same with three generations of, for instance, leptons, the electron, the muon, and the tau. They're absolutely the same from the perspective of the gauge interaction, a feature we call universality, and it's really hardwired in the standard model and most of its extensions. Yet there are differences. They have a different mass, we know. Okay, so this is something we also measure. But in kinematic situations where this mass effect is really negligible in the standard model, we have very clean predictions. We test the standard model with one of its features, that's universality. And that's actually challenged at the moment. And this is what all this excitement about the anomalies comes from. It's not just a deviation, a bump, a hint or something. It's something that touches really the heart of the standard model, and it touches also this flavor puzzle that is always a bit the elephant in the room when you do particle physics. You say, we measure these parameters, but they are kind of structured, but nobody knows who ordered this. Or it's not that nobody knows, it's people have ideas about the origin of flavor and very nice models, but there are many models, and to make progress and to select models or rule out models, it needs new physics. And I think that it needs new physics to progress here is what everybody probably agrees on with the flavor puzzle, with the flavor problem. Okay, so yes, so this flavor puzzle is still there, but what makes these present anomalies interesting is that they are actually touching it. So it could be that it actually helps us to continue. Okay, so flavor is of course not just a puzzle, it is also a window to beyond the standard model physics, which has been realized long ago. It's an amplitude, a flavor changing neutral current amplitude is suppressed by many mechanisms in the standard model. It's loop induced, it's the weak interaction, it has CKM suppression, there's the Jim mechanism, and so on. So when something in the standard model is very, very small, it's an ideal place to look for new physics, because it doesn't have to compete with a big background. And one observable, which is of course highlighted at the moment, is these RK or RK star and friends. All of these B anomalies, observables, they are in FCNCs, they are suppressed in the standard model. But nevertheless, we are having hints of deviations from the standard model there. And these hints, they tell us a bit that it's not a small deviation from the standard model that we are seeing. If these hints in the B2S transitions are there, it's something like 10 or 20% at the level of the amplitude. So you have really to invoke, I would say, a lot of new physics to explain these, okay? But after all, it was all we have been setting out, like maybe 20 years or even earlier, to test the standard model with B2S decays, because they are suppressed in the standard model, so you don't need a lot of new physics to come up. So this is, of course, showcasing here this beautiful result here from the LHCb collaboration on this evidence for RK, for universality violation. So what this tells us, it is a comparison between branching ratios, B2K mu mu versus B2KEE. So you're comparing the same thing, but different leptons, okay? And you can define this for kaons, or K stars, and you can do it with B sub S to phi and so on, or inclusively. But there's this beautiful new measurement by LHCb, which they actually have in a single measurement more than 3 sigma. Okay, and it tells us that muons and electrons appear to be more different than we expected. Okay, so it means an apple and a banana is more. It's more than just fruit. It's a whole new thing. Okay, and this is what sparks all this interest in these observables, okay. And it's not the only anomaly that we are having. So I would say these days are really gifted. Within the last few months, we had 2 anomalies strengthened in this field, in particle physics or in flavor physics. And one is RK, and the other one is also the strengthening of G-2 in the muon sector. So this is a little bit on the slide. It's a bit of a very brief, I mean, snapshot of the anomalies. And I mean, this is a vast topic, and you have to make some selections. So there's something in branching ratios already mentioned by Guy in B2S mu mu decays, but also in the angular distributions, and you can do together a global fit. Okay, and this global fit shows some deviations at, I mean, a few sigma up to 7 sigma, depending on your assumption on hadronic uncertainties. Okay, but I think everybody agrees it's not fitting. Okay, it's not perfect. There is something that needs to be definitely sorted out. And if you see 7 sigma, I mean, this is quite a lot. Then there are these ratios of branching ratios I just mentioned. You're comparing muons and electrons. There are also branching ratios in charged currents, which are not perfect with the standard model. And this shows a deviation of taus from the other leptons, okay? And on top, there's this G-2 of the muon, and also there's an anomaly in the electron, at least in the electron data. So if you look at this as a whole and you try to identify a pattern, you would say, well, there's a common denominator and there's something with leptons. Something is odd with leptons, okay, and low energy data. Okay, so let's address this, okay? Let's address this. Okay, so in terms, if you are a theorist and you want to do models, then it means you need to do some flavorful model building, okay? And also, if you want to do fits, you need to do flavorful fits. In particular, it means that you shouldn't be averaging muons with electrons, because we are just after the differences between muons and electrons. So you need to do everything, the measurements lepton specific, and you have to do the fit lepton specific. And we are, of course, waiting for lots of data on electrons in the future, in particular from Bay2. Okay. So this is this lepton universality, again, with this basket of fruit, and a bit in a snapshot. RK has been measured by LHCb. There are older measurements, but they are consistent by other experiments, but they were consistent with they had large uncertainties and were consistent with the standard model. There's also RK star, and that's where everyone is, I think, waiting for an update of that number. In particular, because the combination of these two observables is very diagnostic on which operator or which model actually induces these anomalies. Okay, so that has been an enormous impact when it has been measured first time in 2017. Okay, RK and friends, they had an enormous impact on model building. After all, they are suggesting there's this generational structure that we see in leptons, but maybe also in other particles in the standard model. They may be more different than we thought. So to make this point even stronger, this is a sketch of a BSM model space from 2002. So it's almost 20 years, okay? And if you look at this, there were models with, there's a lot of SUSY guts, effective SUSY, the MSSM with large and low 10 beta, and some specific SUSY breaking scenario, and little Higgs and extra dimensions. And these models, they had goals, and they were addressing in particular aspects of the Higgs sector, and of course other things. But I would say since 2014, different models have appeared, and they are designed to address these anomalies. They are data driven, okay, and it's clear that when you think about a contribution, 10 to 20% contribution to a rare decay amplitude in the standard model, you better do it with this tree level, because then you can get a big effect without making the mass too low, when you would perhaps be run into problems with collider searches. So there are two possibilities. I would say it's a T channel and it's an S channel diagram. You can invoke leptoquarks, or you can invoke Z prime models. Okay, these are really the main players at the moment, and they're variants of a very beautiful model building. There are also attempts how to get this, which I would say it's at first it seemed a bit ad hoc. You just invent them because they are inducing the right operator and they do the job. But of course, for theory, it's important to also have models that actually have those particles in the spectrum with the right size of coupling and mass. Okay, there's a lot of activity. There's also searches for these particles and then signatures. Okay. When you have lepton non-universality, you generically have also lepton flavor violation that had been pointed out quite soon after RK came out. And in terms of a leptoquark, this is kind of obvious. So a leptoquark is a particle that couples quarks to leptons with a matrix, a coupling matrix, okay? And it is 3 by 3. It has 3 generations of quarks and 3 generations of leptons, and the leptonic coupling is in the columns, and where the lepton index and the quark index is in the rows. And there's no argument a priori why this should be why the leptoquark should couple these to muons and strange to muons, okay, and not also to electrons. So it requires model building, and at that point, this is also an opportunity, okay, because when you think about flavor and flavor models mostly in standard model context, then you have to reproduce a Yukawa coupling. So you have a Yukawa coupling just for quarks. Only quarks couple to quarks and leptons to leptons. When you have leptoquarks, when they actually exist, you get really a nice window into a different type of animal. You get structures that mix lepton flavor and quark flavor in one coupling. So since you need different tools to predict or to obtain the hierarchy structure in the quark sector and the CKM mixing matrix, you typically, for instance, with U1 Froggatt-Nielsen symmetries, you get these hierarchies. You would need something different for the lepton sector, where the PMNS matrix is not hierarchical. I mean, it is more like it has zeros and ones, which is why there's this very common model building with these discrete subgroups of SU3. So in some sense, you would need then, you have an overlay of quark structure, which is hierarchical in the rows, and something like zeros and ones in the columns. So if this is indeed, probed experimentally, it would give a lot of feedback on how flavor has been originates. Okay, so, but a bit more condensed. Okay, so these flavor anomalies, they are several, but let's focus on, I would say, the most bizarre of them or most intriguing of them. And this is this breakdown of lepton flavor universality. Okay, so assuming for the moment that this actually is really, really true, so it's not just 3 sigma or some hint, okay, so it really substantiates, okay, it is a phenomenon. It is something like, well, lepton flavor universality is then broken. So it is like a CP violation. Okay, so it should not just sit only in RK star. It should also in other sectors. Okay, and that can be exploited further. So it also gives, in this sense, a direction where one can look for more tails, okay, more whales. So do some more whale watching, okay. So, and the key to this are these 4 fermion operators, semi-leptonic 4 fermion operators. So when you think about a low energy perspective or a weak scale perspective, when leptoquarks are new physics, degrees of freedom are maybe of the order TeV or higher, you would integrate out these mediators here and you would create 4 fermion operators. Okay, and these operators you can constrain from LHCb's measurements. Okay, you get an effective coupling between a B quark, a strange quark, and 2 leptons, and that points to something. It's dimension 6, so you get something that's suppressed by it's approximately 1 over 40 TeV squared. Okay, so if the coupling is small, you can see these degrees of freedom at the LHC. If the coupling is order 1, well, it'll be 40 TeV. Okay, we need more machines, but it doesn't have. I mean, this is the information you get when you measure a Wilson coefficient. You only get the combination of coupling squared over mass squared, and you need more to resolve that. So, but after all, these are then Wilson coefficients that are probed, and these are Wilson coefficients of operators for fermions, 2 quark fields and 2 lepton fields. Okay, and what we get from analyzing the data, there's a preference that these quarks are actually SU2 doublets, and there's a lot of support that the dominant effect is also in the lepton doublets. Okay. So these type of operators are induced. This is a hint, or this is something that that data suggests. So now, of course, this can be exploited, and the way to do it is to observe that these doublets, they have an up type component and they have a down type component. And the lepton doublets, they have neutrinos and they have the charged leptons, the left-handed charged lepton. So once you switch on this operator, you have links with dineutrino final states and also the up quark sector. And of course, this operator in principle has 4 flavor indices. Okay, so it's huge. So, but I would say it's a big opportunity to look for these type of structures. And the first example I want to talk about where this can be shown and that is very fruitful synergy is with the top sector. Okay, so these 4 fermion operators, these are shown here as these fat blobs. So this is a different operator. This is a 4 fermion operator. And this one is what you would, for instance, probe when you had an E+ E- machine that can produce TT bar pairs. Okay, so it's LQ, it's the lepton and it's the quark operator. And it comes with a minus here. And because there are 2 of these operators that have different SU2 contractions, and minus means it's the difference of these 2 operators. So when you had only this process, you would only probe the difference. When you do B physics, so B to S mu mu, you probe the opposite or the orthogonal combination. You're probing the sum C+, okay? So when you do only B physics, you can only probe C+, and there's a flat direction. You are not able to probe C1 and C3, but you can only probe C+. So you need something to resolve this. When you use different sectors in the fit, you can remove flat directions, and there's an absolute benefit. There's also a process that has not been observed yet, but I think it's really eagerly awaited, and that's B to S neutrino antineutrino, because it has a different leptonic SU2 contraction than B to S L plus, L minus, and therefore it also probes C minus, okay? So when you do all of this together, there's a lot to be gained. So to summarize, so the B anomalies B to S mu mu is measured by LHC, I mean by various experiments at the LHC, and it probes RC plus. What we haven't observed, I would say it's hopefully very likely. I mean, I think it's expected that Bell 2 is observing one of these modes and one of these exclusive modes. It probes C minus, and then of course this is if we have a future collider with electrons, for instance, click-like or any other, it also probes C minus. So it means that there's a link between these sectors that can be exploited, and I would like to talk a little bit about that. So to do a fit between top physics and B physics, you need to make some flavor assumption. And the fit I'm reporting here on is, I would say, quite involved. We were fitting 11 operators, and these are these so-called penguin operators, and they are dipole operators, but they are also these semi-leptonic 4 fermion operators. And this is this OLQ1 and OLQ3. These are the ones that really are in the heart of the in the center of the interest, because they are so closely related to the B anomalies. So things get, of course, complicated, as I mentioned, because of flavor. Okay, these operators, they have Wilson coefficients, and they come with 4 indices, and each goes from 1 to 3 generations. So 2 leptonic type flavor indices and 2 quark type flavor indices. So let's spell out the assumption that one needs to make progress to exploit synergies between top physics and the B2S anomalies. Okay, so to do that, we sat down and selected a pattern, a simple pattern as a benchmark to check whether there are actually anomalies that can be made, synergies that could be made. And this is the so-called top Philic pattern or beauty Philic pattern. It's only, we have a Wilson coefficient matrix in the quark vector. We only switch on the 3rd generation coupling, okay? And when you then look at this matrix, it just means there's just this lonely one in the bottom right, okay? And we chose this for all the operators, okay, for the quark currents. So how do you get a connection with B physics where you have to consider the CKM rotation? And that means that when you go to the mass basis, you are probing still with this 1,1 element, here shown in blue, or numerically here. You're still probing the top sector, but from this rotation, you also get a connection to the flavor changing neutral currents to the B2S sector, okay? So it's the same Wilson coefficient, it's the same entry here, okay, but it feeds into top physics and at a reduced level into B physics, okay, and that can be exploited. Also, some comments are necessary for lepton flavor, okay? So the data today that we are looking at are mostly for muons. That's just because there's the experiments that we have at the moment are performing just really beautifully for muons, and that means when we take the data for the B anomalies, it's essentially lepton flavor specific. Okay, there's a notable exception, and this is once you consider the inclusion of dineutrino modes, because with dineutrino modes they are flavor summed. There are all kinds of neutrinos inside. Nobody is tagging them at a collider experiment. Okay. So when you want to include these dineutrino data, okay, you need to make some assumption, okay? And we did some assumption, and we assumed lepton universality. Also, I said it is maybe it is even broken, but it's just to make progress. One could do it better, but one can test more things. But just for the purpose of this fit, we assumed that. But that's whenever you have dineutrino modes, you are touching the assumption whether something is universal, something conserves lepton flavor, or maybe lepton flavor violation is switched on. Okay, so that's also an interesting point. Also, one can also repeat it with different assumptions. Okay, but as long as we don't include dineutrino modes, it is no problem. Okay. So for the future, of course, it would be wonderful to have all kinds of lepton-specific fits. So not just do it for electrons, do it also for muons, and maybe do it also for taus. Okay. We also considered these click type setting, and that's an E plus E minus collider, but that means we focus on electrons, okay? But in principle, you can also do it lepton specific if you have given sufficient funding, and you can do it also with your initial state. You can do it with muons, okay? Okay, so let's do a global fit. Let's connect top physics and B physics because of these 4 fermion, semi-leptonic 4 fermion operators. And the Wilson coefficients we are interested in, and these are these here, okay? These are the Wilson coefficients, and they're constrained by B physics data and by a future linear collider, okay? But in the fit, there are all these 11 operators, and it's part of that. Okay, so again, this is a brief sketch of the processes that we considered, and the operators that are probed, and in red here the highlights, because these are really the agents of these anomalies at the moment, the 4 fermion operators. Okay, you can do a fit. This is to prove that our setting was okay. This is still in weak effective theory, and you see in C9, which is one of the Wilson coefficients, there's a shift away from the standard model. So we recover the hint for new physics in C9 that many other groups also find in their fit. But of course, we have to make it in SMEFT, in the standard model effective theory, because we include also top, so we can't integrate out the top and the W and so on. And that's the same fit. This is just B physics observables, okay? So we just take note, we constrain 8 Wilson coefficients, okay? And these are the semi-leptonic ones, which have strong constraints. They are the best constraints are on these coefficients, okay? Let's see how it looks like when we include more stuff. When we include the top sector, things look much, much more bright. The semi-leptonic ones are still very nice constraint, but the constraint, the other Wilson coefficient went down. Okay, and this is the money plot. This demonstrates how complementarity works. So the gray bounds here, the gray areas are B physics in the plane of Wilson coefficients, and the light blue ones are top physics, okay? And they are not just complementary, they are obviously even orthogonal, okay? So this is now a little bit of a movie. You can go on and think about in the near future. So Bell 2 will be running. And the big difference from Bell 2 is that we assumed that B2S nu bar, this dineutrino modes will be observed, okay? And we also considered this high luminosity option for the LHC. So blue is today and red is what we can get in terms of these Wilson coefficients. So bounds considerably got better here, but there's a qualitative difference. Now we can constrain 9 coefficients because we can resolve C1 and C3. Previously, we only had C plus from B physics. Okay, so things can get even better when you think about, okay, you consider an E plus E minus machine, which can again probe these orthogonal combination C minus. So this is just our input, and that's what comes out. Okay, so for comparison, so light blue is the future, the near future. This is Bell 2 and the high luminosity LHC. Okay, so this is what we can expect in a few years. Gray is click an E plus E minus collider alone, and blue is what you can get when you combine them. And you see that in particular here in these semi-leptonic operators, there's a lot of progress that we can get. So there's a lot of synergies. Okay, and what it means in terms of the anomalies that we see, well, this is the same. So the first line is today, the second line is in the near future, and the third line is far away, including an E plus E minus collider. So these are our Wilson coefficients, C1 and C3, the one where only one combination we are probing with B2S mu. The star is the standard model, and it's clear there's a flat direction. So in the near future, we can break down this flat direction, but still, this is we have an ambiguity. There's a near standard model solution, and there's a far away solution. But in the future, it may be that these anomalies may become visible also in these methods. So this is the standard model, and this is far away. So I have one more comment. I'm not having the time to discuss this, unfortunately, but I also wanted to talk, like both previous speakers, a little bit on charm physics. And the charm context is that charm physics has very large hadronic uncertainties, but there are also great opportunities for null test in charm. And one null test is when you think about a charm, the rare charm decays into dineutrinos. So B2K nu bar, we talked about this. This is a normal behaving branching ratio. In the standard model, there's something like 10 to the minus 6 branching ratio. Okay, but in charm, these processes are severely Jim suppressed. So there is no observation. There's not even a search reported for any of these semi-leptonic C2U nu bar modes. All of them are null tests. So whatever you see is new physics, okay? And on top of that, the idea that has been reported in these two papers tells you, depending on where you would see a signal, in addition, you can probe lepton flavor universality or charged lepton flavor conservation, okay? And the trick is that you are adding any branching ratio in these sectors, whether it's D to pi nu bar or lambda C2 proton nu bar, okay? It's always a sum of these different final state, and what comes in here is a sum over all these flavor Wilson coefficients, okay? And that depends on what you assume on your flavor, whether it's universal, you have only diagonal couplings, but non-universal, or you allow for a generic structure. That means all hell breaks loose and you have a lepton flavor violation. And the branching ratios that you can expect at the present are actually kind of sizable, okay? So the example here is D plus to pi plus nu bar. The present limit, which is data driven from the charged modes, is it's 2.5 times 10 to the minus 6. That's the upper limit if universality holds. If charged lepton flavor violation holds, the upper limit, it's 1.4 times 10 to the minus 5. Okay, and there's even a model independent upper limit, and then that's 5 times 10 to the minus 5. So there's all these rates are kind of sizable, and it would be lovely if somebody would have a look at those. Okay. With this, I would like to summarize that the present anomalies, they are seen in semi-leptonic BDKs. They challenge universality, and that means also they challenge the standard model. And it has been a huge impact on model building and also on searches. At the LHC collaboration, there are many new searches that people undertook because of these anomalies to cross-check that, in particular in leptoquarks and Z primes. And of course, we are really eagerly awaiting updates on these observables from LHCb, but also from Bell 2. There are also new ideas to test universalities and lepton flavor conservation. It works actually with dineutrino modes, which is a bit of a surprise because dineutrino modes, you don't take the flavor. How can you probe a feature of lepton flavor if you don't measure it? And that's what you can do with rates. And I think that would be lovely if somebody would actually check this, because the actual rates are kind of sizable. So the other idea I would like, I did talk about we are on this to exploit a bit that we have these semi-leptonic 4 fermion operators that where we know their strengths from the B factories, from the B anomalies, and they can connect also, of course, to other sectors, such as the top sector. But of course, more can be done. But I think it's really important in these fits. There are lots of SMEF fits, but if you want to connect to the B anomalies, you have to take the semi-leptonic 4 fermion operators. And yes, and I think, and I agree with all the previous speakers who also didn't just talk on one topic. They also had B physics, they had charm physics. I didn't have kaon physics, but I had top physics. And I think it really highlights that flavor is broader and I would say more exciting and fun than ever. So thank you very much.
Thank you, Gudrun, for this great talk. Let's take a bit of time for a question or two, maybe at the end. Let me start asking a question. So in this connection you made with top physics, as far as I understood, you focused on operators with TT bar. Can you also look at operators which have flavor change in the up sector, so that would lead to rare top decays or things like single top production at E plus E minus collisions? Is this something that is interesting in this context?
Yes. Okay. So of course we had a simple flavor pattern, and we just turned on in the top sector in the up sector the TT bar coupling. But you can make more. You can fill this matrix and make a fit, and there's a reason why we didn't include single top production, and that's because then you would need more operators. There are two topics why we didn't do it. Okay, so first of all, when you start invoking them, you need a whole bunch of more operators. But also when you look at the data on single top production, I mean, what's the data? They are distributions. And when you have distributions, you have correlations between the different bins, and they are not publicly available. And we, with a collaboration, we did this. We have a paper where we discuss the importance of such correlations. So we didn't know what to. Yeah. So in principle, it can be done, and I think it's interesting. It should be done, but we need the correlation. We need the correlation from. When the experimentalists they publish their distribution, they should also provide the bin-to-bin correlation, because otherwise there's a lot of uncertainty. I mean, it really it qualitatively changes the result of the fit when you switch correlations on or off, and that's why we didn't do it. But in principle, this can be made much bigger. There's no limit, okay, but the correlations, they need to be important, taken into account.